And the error was toward the end, fortunately. Okay, so if you'll recall, we had that pi sub I plus 1 should be, I think it's p over 1 minus p times pi sub I. Can somebody verify that? That's what we had from last time, right? Okay, and then we also have that the sum from I equals 0 to n of pi sub I has to equal 1, and probably capital N. We had up to n states. Okay? And then this gives us that let's see, pi sub 0 times this sum equals 0 to n of p over 1 minus p to the I equals 1. And then I made a mistake here. This should equal 1 minus, let's see if I get this right, p over 1 minus p to the n plus 1 over 1 minus p over 1 minus p. Okay, I think the problem is when we sent n to infinity. When n goes to infinity, pi naught becomes 1 over that quantity, which becomes 1 over 1 over 1 minus p over 1 minus p, which equals 1 minus p over 1 minus p, which should be 1 minus p over 1 minus p. So it's 1 minus 2p over 1 minus p. I think last time I said it was just 1 over p, or p over 1 minus p. Anyways, that's what it should be. This is the correction. Okay, and if you remember, we went through a pretty elaborate description of why this relationship holds true, and there's a simpler explanation. I wanted to go through that quickly. And it's called the balance equation, or the balance phenomenon. Okay, where this was the relation that we had, right? And the point is, remember, if you think about what happens in the steady state as time goes into infinity, you spend a fraction of time, or on a given tick, right, in the discrete case, there's a probability pi I you're going to be in this state, a probability of pi I plus 1 you're going to be in this state over here, right? And so the thing to notice in this Markov chain is the only way to get between these two states is by taking these transitions, right? There are no, if you remember, we have this chain. There are no transitions that sort of leap from one side to the other. I mean, that's possible in a general Markov model, but in this Markov chain, it's not the case, right? Only adjacent states have transitions. There's only transitions between I and I plus 1 for all I, right? So every time you go across this transition, you can't take it again until you take one of these, right? So they get taken roughly the same number of times, plus or minus 1. When you go to infinity, it doesn't really matter. So the probability that you take this transition on any given time tick. Okay, so maybe I should write all this down. Right. So in this long chain, we got these transitions here. Right, the point is pick any pair to take this transition here. To take this twice, must take this once. Right, there's no way to take it twice without taking this one, because you got to get back over to this side before you can take it again. Okay, so what? So they get taken same number of times. Okay, so what that says is, well, let's see. Okay, well, why don't we do it out formally? That says let n1 of t be the number of times. Well, let's do n sub 1. We go I to I plus 1 by time t. And let's have m. Why do 1? Yeah, let's make this I. N sub I of t, m sub I of t. The number of times we go I plus 1 to I by time t. And let's, well, you could do it this way. So what I'm saying is E of, how do I want to say this? Yeah. I'm claiming this. The limit is of E of NIT equals the limit as t goes to infinity of E of MIT. The expected number of times I take the transition going to the right is the same amount of times I take the transition going to the left as time goes to infinity. So why did I do that? Okay, yeah. So let's call this. You have to trust me. You can move the limit to the inside here. So let's call this E of n, and this will be E of m. Okay, so E of n equals E of m. All right. So what is E of n? Damn it! Don't do that. Hang on. Forget this. Let's look at Ni of t, for instance. Let's let this be equal to the sum of xij of t, where j goes from 0 to, get rid of the t. J goes from 0 to t. Yeah. Where xij equals, is an indicator random variable, equals 1 if at time j go from state I to state I plus 1. Okay, 0 otherwise. And yij equals 1 if at time j go from state I plus 1 to I. 0 otherwise. Okay, so that's Ni of t. Mi of t is going to equal this sum. J equals 0 to t of yij. Okay? And E of Ni of t is just switching the, well, E of the sum of xij from 0 to t, which is the sum from 0 to t of E of xij, which is just going to be t plus 1 times the probability that at time t you're going from state I to I plus 1. So that means that you have to have started in state I. That happens with probability pi sub I, and you make that transition to the right with probability p. Right? And E of m I of t equals all this, e to the sum of the yij, which equals blah, t plus 1 pi I plus 1 of y minus p. And I use that balance idea that in the limit, this has to equal this. Okay? So limit as t goes to infinity of t plus 1 pi ip equals t plus 1, again the limit, pi plus 1 times 1 minus p. And the only way that can happen is t grows very, very large. And the limit is if pi ip equals pi plus 1 times 1 minus p. Okay? So just a very formal way to show you intuitively that pi I is the probability you're in, sort of the fraction of time you're going to be in that state I. Pi plus 1 is the probability, the fraction of time you're going to be in state I plus 1. And basically, the amount of times you're going to transition from this one to that one has to equal the amount of time you transition back. So this explains that intuition. Or to put it another way, okay, imagine I tell you that you spend, that pi I equals 1/2. And that pi plus 1 equals 1/4. Or let me not do that. Let me do it this way. Pi I is the fraction of time you're going to spend in that state. Pi plus 1 is the fraction of time you're going to spend in this state. Or, you know, for a given tick t, pi I is the probability you're in this state. Pi plus 1 is the probability you're in that state. Okay? And let's say p is 0.99, and 1 minus p is therefore 0.01. Okay? And you have to take these two things roughly the same amount of time. Okay, these two transitions. The number, because every time you transition here, you have to transition back before you take this transition again. Okay, same reasoning. Okay? So, scratch it. Do people get this? I mean, I'm just going to wind up going through the same thing again. Do people understand what I'm getting at here? All right. IP. Yeah. Okay. In the continuous version. Okay. You have a similar phenomenon. We're going from state I to state I plus 1, and we said you go at some rate exponentially. Some time, you spend some time in this state. I'm sorry, there may be multiple transitions, but you take this transition after a time that's exponentially distributed with rate lambda, and if it's the first transition that you're going to take, that's the time you spend until you take it, and you go back the other way with rate mu. And again, there's some average amount of time you spend in each state that we call pi sub I and pi sub I plus 1, and again, they have something called the balance equations, which follows the same intuition, which is that pi I times lambda equals pi plus 1 times mu. Let me make sure I got this right. Yeah. Okay. Hence, pi I plus 1 equals lambda over mu pi sub I. Okay, it takes a bit of a going from there has to be some sort of intuitive notion of rate. Basically, that this is the rate at which you're going in this direction, and this is the rate at which you're going in this direction. It's not. You have to take a kind of a leap of faith from our discussion of exponentially distributed random variables. But anyway, you could go through and solve it in a similar manner that we solved that over there. Or actually, I should say this. It's the same problem if I just put lambda over mu for each of these, right? That's the probability. We said the probability that you take this transition next is going to be lambda over lambda plus mu, right? There's another transition coming out of this state that goes at rate mu. So you're either going to take this transition or this transition. The probability to take this one is lambda over lambda plus mu. The probability to take this one is mu over lambda plus mu. And same thing for this guy. The probability to take this transition is mu over lambda plus mu. And the probability to go this way is lambda over lambda plus mu, because the transition goes out at rate lambda. Okay, so again, you look at the balance equations, and it's the same problem we look at over here. Instead of p and 1 minus p, you've got lambda over lambda plus mu and mu over lambda plus mu. So it's the exact same thing. Okay, so if you believe it here, you should also believe it over there. Okay? Any questions about this? Okay, something I wanted to cover very quickly, which is very powerful but is also very important, something called Little's law. And Little's law says n equals lambda t, right? Let me make sure I got this right. Yeah. Okay. It always helps to rederive. This is how it's usually written. What it really means, okay, is that n of t be the number of items in the queue at time t. Lambda is the rate of arrivals to the queue. And t is the time, sorry, let's say t sub I is the time the ith item spends in the queue. Okay, then what Little's law really says okay, and also this is any distribution. Okay, Little's law says that E of n equals E of ti, right? So n of t changes, the q grows up and goes down. Okay, lambda is just some average arrival process. You know, look over time infinity, or as time goes to infinity, how many arrivals came over that amount of time. Okay, and t sub I is the time the ith item spends in the queue. So just the average time spent in the queue. So the average length of the queue is the arrival rate times the average time an object spends in the queue. Okay, and rather than just memorizing the formula, it's really easy to remember, right? You have some equation, and you can sort of imagine that as the rate gets higher, okay, the rate at which things arrive to the queue, n is going to grow, right? And the rate at which as the amount of time something spends in the queue grows, also the length of the line is going to grow, right? Think of it like a supermarket line. So a queue is like a supermarket line. Okay, Little's law is also one of those really, really important things I want you to remember. Real important. Okay, you'll see on the homework, well, take another look at problem 1. There's your hint, okay, with the change that I described over there. So for people who came in late and for folks on CVN, if you go to this board over here, all the way to the right, just a fix on problem 1. Santa claims to see 2 children each minute on average instead of, I think I said Santa spends 2 minutes with each child. And it's trivial. You just apply Little's law. But remember Little's law, because in the networking context, it's used in sneaky ways. So you shouldn't have any problems remembering Little's law. And hopefully you'll be able to see where and when to use it. Okay? Any questions? All right, so this ends probability review. And so today we're going to start doing coding theory, simple coding. All right, so everybody's ready to move on? Okay. Okay, so let's look back at this network stack. Okay, again we had this physical layer on the bottom, which is the physics behind sending a bit. And now we're gonna move up to the next layer. We're gonna skip this layer where you deal with disperse. Actually, I wrote them all down. All these terms. Okay, so here you worry about attenuation, distortion, dispersion, noise. Okay, basically, if you took electrical engineering 3701, that's what should have been covered there. Okay, how do you get a bit from point A to point B? Okay, and so we're going to start at the data link layer, where everything is digital. Okay, all zeros and ones. Okay, so we don't worry about any of this analog stuff. Not to say it's not important, it's just that's for another course. This course is all digital. Okay? In terms of the information we're trying to transmit. Anybody here not see the Manchurian Candidate? Everybody, you haven't seen it. Oh, well, I thought it was good. My wife thought it wasn't. But anyway, all right. So let's think about better. What's something everybody would know? People here seen the Ali G show? No. All right. He makes fun of. He's a goofy comedian. He makes fun of politicians. Like he gets real politicians to come on his show and he interviews them and he asks them really stupid questions. Okay, so like I'll give you an example. He asked this former Secretary of Defense. Okay, he asked the guy. I mean, really stupid questions, just kind of making fun of the guy. And he asked him, wasn't it a really bad idea to have Iran and Iraq, countries next to one another, have such similar names? Because suppose you're going to bomb, you want to bomb Iraq. And you get on the mic and you're like, yo, go bomb Iraq, and there's noise. Like, isn't there a chance you're going to bomb the wrong country? And the guy's like, absolutely not. That would never be a problem. And, so stuff like that. Anyway, that's what we're dealing with now is, when you say bomb Iraq, and then there's some noise, right? So there's some bits that are lost. Maybe not the best example. I mean, wartime examples aren't good. So, it could also be like take little, to the doctor. Whatever. But there's some digital information loss. Okay? Or here's a good one that students always appreciate. Your grade for the term was, right? No good. So you can't have this information lost. So what do? So all this information is sent as bits, digital bits, and bits might get lost or corrupted or something along those lines. Okay? So here's some assumptions we're going to make. Okay? We got A and B are going to communicate. Okay? And they know the rate at which bits are sent. So bits are never lost. They just get confused. They just might be misinterpreted. Okay, that's an assumption we're going to make for the course. Okay, meaning that if A wants to send out to B, if it wants to send the signal 10110, okay, and somewhere along the line corrupted, then what reaches B, it's a 5-bit sequence, so we're going to have a 5-bit sequence reach B. Okay, so what'll reach B is 00111. Okay, so the first bit was corrupted and the last bit was corrupted, right? Okay, because if you flip the first and last bits, meaning just flip their values, you would get the same, what was transmitted would also be received. Okay? So in this case, if you send out the message, bomb Iraq, instead of getting static, we'd have to take a guess. Bomb Iraq, right? Take little to the doctor, take little Tina to the doctor. Okay? Your grade for the term was, use your best guess. Your grade for the term was F, right? No, nobody here, right? Everybody here going for an A? All right. Okay. So let's describe this a little more formally. Okay, so A sends a message. M is going to be B1, B2, B sub K, so a K-bit message. Okay, each B sub I is either 0 or 1. Okay, B receives a message. Let's call it A1 through AK. Each A sub I is also either 0 or 1. Okay. Bit I is received correctly if A sub I equals B sub I. Is corrupted. Or I say flipped a lot of the time because we're just dealing with ones and zeros. If A sub I does not equal B sub I. Okay? So what's coding all about? Coding is all about making sure with as high probability as high probability as can. Okay, so suppose the channel, so we're going to be dealing in this class. Channel flipping, channel bit flipping, I should say, is a Bernoulli process. With probability P. Okay, so a bit is flipped IID, so independent and identically distributed with probability P. Okay, so you send a bit, flip a coin, or the channel flips a coin. If the coin comes up tails, the bit's flipped. If it comes up heads, it's not. Okay, and the chances that the coin comes up tails is probability P. Okay, so you just keep flipping the coin. Okay, so suppose that's the case. Suppose you've got a channel that keeps flipping bits, and you want to increase the likelihood that your message gets through. What's the easiest way that we know of to increase the likelihood that the message correctly gets through? Did people understand the question? Did people understand the question? There you go. Repeat. The easiest code is simple repetition. Okay? So suppose I have a message. A has a message, 01101. Suppose A and B both know it's a 5-bit message. Or forget that. Suppose A and B, suppose A has this. Yeah, let's say they know it's a 5-bit message. So what can A do to make sure that B, or increase the likelihood that B gets the right message? A can send the message 3 times, for instance. Okay, so this is the message. Okay, and so here's the send. The coding protocol is send the message 3 times. Okay, so A sends 01101, 01101, 01101. This thing arrives at the other side to B, and it comes out. Let's say bits get flipped with very low probability. So suppose it comes out 11101, 01100, 001. Okay, and so B, what it can do for each bit is, take the first bit. It came out a 1. It came out a 0. It came out a 0. So it came out 0 more times. So probably a better guess to choose 0. It was 1, right? And so one other thing I should say is that P is usually pretty small. Okay, the error rates on channels are not like 50 or 20 or 15%. They're more like 1%, 0.5%, 0.05%. Really small values. Okay, so simple codes like this are likely to work. Okay, so the message is probably, the first bit's probably 0. The second bit's probably, well, it came out 1 3 times, so it's very likely that it's 1. It would have had to have been flipped all 3 times for it to be wrong. The third bit is probably a 1. The fourth bit is probably a 0, and the fifth bit's probably a 1. Okay, so in this case, if B guessed by taking which value came up more frequently, if B guessed 01101, it would be right. Okay, it's possible you could get unlucky and it could be wrong as well. Okay, so for instance, so if the coding protocol is repeat. Repeat transmission L times. Okay, and B takes B computes I'll call it A sub I to be the value that it received for the ith bit the most times. Okay? So what's the probability that B gets the ith bit correctly? What has to happen for B to get the ith bit correctly? The number of bits that should be less than L by 2. Yeah. Okay. Okay? So the probability is just going to be the sum from, let me not use I, let's use J, equals 0 to floor L over 2. Okay. I'm going to sum over the likelihood that exactly J bits get flipped. The bit gets flipped J times, given that I've sent it L times. Okay. So that's just going to be L choose J. I have to choose which J bits are going to get flipped out of the L times. And it's P to the J. 1 minus P to the L minus J. Right? That's the probability that each value in this sum. This is the probability that J out of L bits get flipped. Exactly. And exactly 0 bits getting flipped, all those scenarios are mutually exclusive from the scenario 1 bits get flipped, mutually exclusive from the scenario where 2 bits get flipped, so I can just add the sum of those probabilities. So this is the probability that J out of L bits get flipped, okay, which is the probability that this method correctly produces the right out bit as B's output. Okay? So the more times the bigger you make L, the less likely you are to get tricked. The less likely you are to erroneously return the wrong bit. Okay, but we're also going to be concerned with the efficiency of a code. Okay, so let K be the number of bits of information A wants to send, and let N plus K be the number of bits A actually sends. Now let's just call it N. Let N be the number of bits that A actually sends as its code. Okay, so for instance, if we replicate L times, then N equals L times K. Right? I should say, not if we replicate, if we send the transmission L times. we're repeating it to make it more likely that a correct copy gets through, or that we make it more likely that B can decipher what's trying to be sent. Okay? Everyone with me? Okay. Then the efficiency is defined to be K over N. Am I doing this right? No, it's N over K. That's one over the other. K over N. Okay? So efficiency of 1 is as good as you can get. For every bit of information you're sending, you're going to get a bit of information through, assuming that there's no corruption. Okay? If you're repeating, right? If you're duplicating the message, then for every bit of information I want to send, I'm sending 2 bits out, right? So the information per bit that I'm sending is a half. Okay, that's what the efficiency's telling us. Okay, and so the lower the efficiency, the less utilization you're making of your channel, right? I mean, I have this bandwidth. You know, you all buy bandwidth. Everyone's familiar with it, right? Ethernet's got more than DSL, and DSL's got more than a modem. And you don't want to be wasting this precious bandwidth by sending the information 10 times over just to make sure it's received correctly. It's not efficient, right? So you want to make the efficiency as close to 1 as possible. But probability of failed message or incorrectly interpreted message as low as possible. Okay, and we're going to look at two kinds of codes, or 2 properties of codes. Okay, error detecting and error correcting. Okay, so detecting just means, hey, one of these bits is flipped. There's something wrong in this message. I don't know what it is. Something's wrong. Okay, whereas error correcting says, you know, bits 3, 5, and 4, 3, 4, and 5 are flipped. So you can correct the message. Okay, and this is all being done probabilistically. There's always some probability that you're going to correct it and you're going to do it wrong. There's always a probability you're going to detect it and you're going to detect it wrong. Okay, doesn't matter what you do. Okay, there's always going to be some probability. There's always some outcome that what you're doing could be wrong. You just want to make it. You want to choose the most likely outcome. You want to make it very, very likely that that outcome is going to happen, and you don't want to waste a lot of bits to do it. Okay, so just simple repeating is very inefficient. Okay, send L copies. Okay, gives you an efficiency of 1 over L. Okay, send 1 copy, your efficiency is 1. Send 2 copies, your efficiency is a half. Send 10 copies, your efficiency is 1/10. Become more and more likely to be able to detect or correct the errors, but you're making very inefficient use of the channel. Okay, so what's a more efficient code? Sort of the simplest, very efficient but not very powerful code. So here is an efficient, but good chance of making a mistake. Error detecting. Okay, and it's the XOR code. Okay, so here's what A does. A wants to send a k-bit message. Okay, so whatever. 110, 110, 10. So k in this case is 1, 2, 3, 4, 5, 6, 7, 8. Okay, k equals 8. Okay, what it does is it takes all these bits and exclusively ORs them together. Everyone knows how to do exclusive OR? Has anyone not heard of exclusive OR? Okay, so what is the outcome when you exclusively OR those bits? 1. Yeah, exclusive OR is just the parity. Right? So if you've got an odd number of 1s, it's going to equal 1. If you've got an even number of 1s, it's going to equal 0. Okay? So the exclusive OR, in this case, equals 1. Okay? And now, when it sends the message, A wants to send. A wants to send a k-bit message. What it sends is the message M and the XOR bit. Okay, so A is actually going to send into the wire 110, 110, 10, and then this 1. That's the XOR bit. Okay, and now here's the protocol that B is, yeah, Ron.
Nearly, it's just number of even numbers, number of zeros.
Number of 1s. If there's an odd number of 1s, it equals 1. If there's an even number of 1s, it equals 0. Okay. Yeah. So the point to note is I forget. That's how I draw exclusive OR. I equals 1 to k of b sub I equals 1 if odd number of b sub I are 1, 0 otherwise. Okay? Okay, so here's the protocol they agree with beforehand. Okay, so A sends 8 bits plus XOR bit. Okay? B receives the 9 bits. What does it do? Computes the last bit. No, well, B is going to receive 9 bits. So what do you mean by computes the last bit? You mean takes the first 8 bits, XORs them, checks to see if it matches the 9th bit. Yeah, okay, that's one thing you could do. So B could take 8 first received bits, XOR them, see if that matches the 9th bit. Okay? Or just a little bit simpler and does the same thing. B could XOR all 9 bits. Okay? If the first 8 match the 9th, then when you XOR those two together, you're going to get 0. Always. So B could XOR all 9 bits. And so if A took all of these 9 bits, the 8 here, and the XOR, which was the 9th, since this is a 1 if there are an odd number of 1s and it's 0 if there are an even number of 0s, then including this 9th bit, you're always going to have an even number of 1s for what A generates. So if you exclusively OR all k plus 1 bits that A is going to send, it should always come out to be 0. Right? So on the other side, when B receives these 9 bits, it XORs them all together. Okay? If B could XOR all 9 bits, if this XOR equals 0, if this XOR does not equal 0, then some bit must have been flipped. implies error detected. Right? If it doesn't XOR to 0, sorry, if it does XOR to 0, then no error was detected. Doesn't mean no error was there, just means that it wasn't detected. Okay, so for instance, why don't we do out the example? So you got to imagine bit flipping is very, very, very unlikely. Okay, so suppose A wants to send 110, this value we had up here. So it also tacks on a 1 and sends that over. Let's say it all gets there correctly. Okay, 11011 010 1. Well, whatever this thing XORs to is going to equal this value, and anything XORed with itself is going to be 0. I mean, I'm just repeating in another way what I've said before. So if it's all received correctly, when B exclusively ORs all these bits, it's going to equal 0. So B will say no error detected. And it could pass the message up to the application, that's waiting for this message. I couldn't detect any errors in it. Right? Okay, suppose a bit does get flipped in transition. So let's say this bit here gets flipped. Okay, so the message that arrives at B is 11011 1101. Right? Only that 6th bit got flipped. Okay? When B does the exclusive OR here, it now gets 1. Okay? 1. Error detected. Okay, so it says, whoa, something's wrong. Throws that away and tells the application, ask for the message again because the one that got sent through was definitely corrupted. Okay? Of course, you could also have 110111010.1, and this could be the bit, the check itself, the error correcting bit, could be the one that gets flipped. This could get flipped to 0. In which case, the message is actually correct. But because this bit gets flipped when it goes through, you again get 110111010.0, and again it's going to compute error detected. So you could say it was wrong. There was no error. The error, the only bit that was flipped was the check bit. But for our purposes, there was some corrupted bit in the message. The message being the original information plus the coding bit. So again, it detected an error. Okay, and if 2 bits get flipped, then so for instance, let's say 110111010.1. Let's say these 2 bits get flipped, so we have 1100010.1. It's going to go through, and you're going to do the exclusive OR. The exclusive OR is going to come out to 0. And so it's going to say no error detected. Okay, but there were errors, right? There were 2 bit flips. So the error gets through. Okay, so do people understand what's going on? You have a bunch of this is a 1D parity check is what it's called. Okay, I take a bunch of bits, I compute their exclusive OR, I send all those bits and the exclusive OR. At the receiving end, I get in a bunch of bits, some of which may have been flipped. I exclusive OR all these bits together. If it comes out as 0, then I can't tell whether or not there's been an error. If it comes out a 1, there's definitely been an error. Who gets it? About half. So let me ask this way. So suppose this was received, where this is the original message and this is the check bit. Was there an error? Yeah, Ron. Yeah, there was an error, right? The exclusive OR has to come out to equal 0 if there's no, if there were no errors. So let me not say was there an error. Was there a bit flipped? Yeah, there had to be. Okay. What about if we get 1 0 1 1 0 1 0? Was there a bit flipped? Huh?
Unknown?
No. Probably not. Given that bit flips are very, very unlikely, probably not. But there may have been 2 bits that were flipped. Okay? Okay, so here's the thing about the 1D parity check. It's very easy to figure out what it can detect and what it can't detect. Detects J-bit flips when J is what? 1? Somebody said something else. Odd, yeah. Whenever J is odd. Whenever you have an odd number of bit flips, okay, the exclusive OR, the value is going to flip. If I flip 1 bit, the exclusive OR doesn't work out. If I flip another bit, the exclusive OR matches the original exclusive OR, right? If you flip 3 bits, again, it doesn't match. Okay, so this can detect. We'll always be able to detect an odd number of bit flips. Cannot detect an even number of bit flips. Can't tell the difference between an even number of bit flips and no bit flips. Okay. What's the efficiency of the code? Efficiency of 1D parity, protecting K data bits is what? K over K plus 1, yeah. Right? I sent K data bits, and I sent K data plus check plus K data bits plus a check bit. So for every K data bits I want to send, I wind up sending K plus 1 bits. So the efficiency is K over K plus 1. Everybody see that? Right? If we're protecting K bits at a time. Okay, so the 1D parity is fairly weak. So let me now show you the 2D parity. Okay, suppose I want to send K, which equals let's do J times L bits, where J and L are integers. Okay, so it's a non-prime number. Okay, well here's how I do the 2D parity. Let me write the bits in this way. Instead of writing B1, B2, B sub K, I'm going to rewrite as in a 2-column form. B1 comma 1, B1 comma 2, dot dot dot, B1 comma J. Okay, and then I'll start with my next column, next row, B2 comma 1, B2 comma 2, B2 comma J, and I'll keep doing that until I get up to L. BL comma 1, BL comma 2, BL comma J. Right, so I have L times J bits. I've just reordered re-index them. Okay? And I'm actually going to lay them out in that format. So just to rewrite it, I'll rewrite it bigger. B1 comma 1, B1 comma 2, B1 comma j, B2 comma 1, B2 comma 2, B2 comma j, all the way up to BL comma 1, BL comma 2, BL comma j. Okay, so those are my original bits. And now what I'm going to compute here is the XOR of the B sub 1 comma i's. Right, I goes from 1 to j. Over here, the exclusive OR of I from 1 to j of B2 comma I. Okay? Everybody with me? You know, etc. Over here, the exclusive OR of B L comma I. Okay, and let's call this C1. This will be C2. This will be CL. Now, I'll also do it vertically. I'll do the exclusive OR of the B sub I comma 1, I equals 1 to L. Okay, over here, the exclusive OR I equals 1 to L of B sub B of I comma 2. Okay, over here, the exclusive OR I from 1 to L of B of I comma j. Let's call this D1 through DJ. Okay? So I just took the exclusive OR of this row, put the value here. Exclusive OR of this row, put the value here. Exclusive OR of this column, put it here. Exclusive OR of this column, put it here. And over here, this very last one, I'm going to take the exclusive OR of this column here, okay, which happens to be the exclusive OR of this row with this row with this row with this row with this row, okay. It also happens to be the exclusive OR of this column with this column with this column with this column, right? It's an exclusive OR is associative, so it doesn't matter what order you do it in, or it doesn't matter where you put the parentheses. So if I exclusive OR all these bits together, that's the same as exclusively ORing these bits together. It's also the same as exclusively ORing these bits together. So this here is just going to be, you know, the double exclusive OR of I equals 1 to j, h equals 1 to L of B sub I comma h. Everybody see what I'm doing? Okay. And now A and B arrange in advance that they're going to use the following protocol. A will send B11, B12, right up to B1J, then B21, then B22, up to B2J, right? Keep doing this up to BL1, BL2, right? BLJ. So it's sent all the data bits, and then it's going to send C1, C2, CL, then D1, D2, DJ. Let's call this final thing. Let's not use A. We're using A. Let's use A. What the heck? And then finally, it's going to send A. So it's going to send all these bits. Okay. Just it's going to send them in that order. It's going to be beforehand. A and B are going to agree upon the size of L, the size of J, and that the bits are going to be sent in this order. So B receives B11, let's just use primes. B11 prime, B12 prime, B21 prime, B2J prime, right? BLJ prime, C1 prime, CL prime, D1 prime, DJ prime, A prime. Okay, so all the bits that were sent, B receives them. They may be corrupted, where x equals x, x does not equal x prime if bit is flipped. X equals x prime if bit received correctly. So everybody gets what I'm doing here? No? I'm just calling them primes because they may have been flipped, they may not have been flipped. Okay? Okay? So when B gets all these bits, right, you're sending them down this channel. When B gets them, it places them into a similar tabular form. Okay, so B receives these bits, places them on a similar table. Okay. B11 prime, B12 prime, B1, what I say, L or J? J, L, J prime. And I can also put C1 prime here. Okay, B21 prime, B2J prime, C2 prime. Okay, BL1 prime, BLJ prime, CJ prime. Sorry, CL prime, and D1, DL prime, A prime. Okay, so it just took everything it received, all these bits, got them in a channel, and just put them back in its own table. Okay? What does B do to check correctness? What does it do to check correctness of the received code bits? It has to hold true if the bits are received correctly. Huh? Okay, B checks A prime, and what should A prime equal? But B doesn't know what A is. That would be true if everything was sent correctly. But what can B check here? Huh? How do you check the C's and D's? XOR what? Yeah, right? I mean, C1 was supposed to be the exclusive OR of the bits in this first row, right? That's how we computed C1. So C1 should equal the exclusive or C1 prime. If things were sent correctly, then C1 prime would have to equal the XOR of these bits. Or in other words, the exclusive OR of this entire row, including the C1 prime, should equal 0. This 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 should equal 0. Okay? Also, the D1 primes. This should equal 0. 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 And the exclusive OR of all these bits should equal A prime. Or equivalently, If all these matched up, then it's enough just to check this, that these exclusive, this column exclusive OR equals 0, and this row exclusive OR equals 0. So if can check correct receipt by XORing all rows and columns. Okay, so for instance, suppose you get this. Suppose you agree we're going to send a 4x4 bit message. So 16 bits, 4 rows, 4 columns. This is what B receives. Are there any errors? Are there any bit flips? Well, we can't tell. From as much as we can tell, there are no bit flips because every row and every column exclusively ORs to 0. Right? How about now? Are there any errors? I mean, you just saw me change the bit. So, yeah, there are errors, right? Because this row and this column no longer exclusively OR to 0, right? So there must be an error. But not only that, there was just one row and one column that didn't exclusively OR to 0, right? So if I change the bit that appears in that row and that column, if I flip that bit, then all the rows and columns will XOR to 0, right? So if it's very, very, very unlikely that bits were flipped, suppose I told you that only one bit was flipped in the transmission of this message, it would have to be this bit. Right? This is the only bit that if I flipped it would then make this code possibly correct. Okay, hence, this is the bit that was probably flipped. Okay, it's possible that some other sequence of 3 bits flipped or some other sequence of 5 bits flipped, but if only one bit flipped, it has to be this one here. Because by flipping it back, that's the only way I get all the columns and rows to XOR to 0. So this is also a 1-bit correcting code. Okay, if only one bit flips, my routine, which is to look for the row in the column in which things don't look right and flip that bit back, that will also correct the 1-bit error. Okay, so let's do another example. Let's do 2 more examples. Okay? Is the code correct? Is it Akshay or no? Faisal, sorry.
I don't understand why it's only a 1-bit correcting code. Can it, if more than 1 bits are flipped, can't it detect those errors as well?
Well, let's do that next. I'll show you why it's only 1-bit correcting code. But first, is this a correct transmission? No, why not? 3rd row? Anything else? 2nd column, yeah. So which bit probably flipped? If there's a 1-bit flip. Yeah, this one right here, right? This was probably a 0. Because if I make it a 0, everything works okay. Yeah, Ron.
Then wouldn't the bottom 0 below the line, wouldn't that have been a 1? Wouldn't that
If this would have been a 0, now this would be, right? 1 XOR 1 XOR 0 should be 0. It didn't work out right. Hence it helped us detect the problem, location of the problem. Okay, so let's do one more example. Is this code correct? No. Why not? Second column and third column both. So at least 2 bits flipped. So Faisal, which 2? That's right. Could be the 2. I mean, the 2 bits have to flip in the same row, but it could have been in this row or this row or this row or this row or this row, right? So we don't know. So it can detect 2 bit flips, but it can't correct. Okay, so here's something to think about, and you're going to have to think about it because it's part of the homework. Whose due date I will push back even further because we still haven't gotten to linear Hamming codes. But nonetheless, you can at least do everything except the last 3 problems. So this can always detect a 1-bit flip. It can always detect 2-bit flips, but can't always correct them. So you can see why it can't. Here's an example where it can't always correct them. Why can it always detect them? Okay. Why can this? Okay. Now about 3-bit flips. 4, 5. Okay, in fact, I think I asked this on the homework, right? Yeah, prove that any combination of 1, 2, or 3-bit errors is detectable. Okay, prove it. For 16-bit data word, show a 4-bit error combination that cannot be detected and show one that can. Okay, and then fun with probability after that on that question. Okay, so you should be able to do those questions. You shouldn't be able to like knock them off in 10 seconds, but sit down and thinking about it, you should be able to do them now. Okay, I will have office hours this Wednesday, and also tomorrow, right? Tomorrow 4 to 5, Wednesday 11 o'clock, right after class. Yeah. Okay, so that's it. Sorry? Has it been corrected yet? No. I mean, it's been given out, but it hasn't been given back to me yet. So I'll look into that. Yeah, Sebastian.
We'll just do a Wednesday.
Now do Wednesday. Move back.
It was due Wednesday alone, no? It was already due Wednesday.
Oh, the next one. Sorry. Next one. Okay, next one.